All right, people filing in the door. Happy Halloween, everyone. Happy Halloween. Hope you got some goodies. Miss Dean brought me a little Halloween goodie this morning. Thank you, Aaron. Brought me a little Halloween goodie this morning. Set it on my desk while I was in my 0 hour class. So got my little ghost full of sweeties or Smarties, I guess those are called. So yeah, I'll be having me a little treat throughout the day. So hopefully you have some little goodies around there. Got some candy to hand out tonight. And if you bought candy to hand out tonight, I hope you bought too much because, it's leftovers. Yeah. It's always great to have leftover Halloween candy. So we bought a big bag of candy. And I think last year we only had like 7 or 8 trick-or-treaters. So I should have a lot left over. Be enjoying myself today. So tonight I'll be sitting around, hand one out, eat one. Hand one out, eat two. Hand one, however it works. It'll be good. All right, man. We got a lot to cover today, but then we'll get there. I'm going to put this up first before we get into which jack-o'-lantern are you today for Halloween? What's your day shaping up to be here? Look at the chat there. And while we're working on this, let's 1, 2, 3, or 4. If it gives us that little squiggly, let's correct some spelling. I started out the day somewhere between a 2 and a 3. 2 is kind of close to a sleepy one, because you don't want to open your eyes. You're just kind of like dead to the world. 1s, 2s, 3s. A few 1s, a few 2s. 2s is kind of leading the way here. 1 or 3. Not really any 4s today. I think about all the candy tonight. I'm a 1, but most of the time I kind of live in the 3 world. I think I'm just going a bunch of different directions. Busy. Well, just a little fun thing to start your day there. So let's get over to the stuff we're here for. Let's see, we're here for 5th hour. There it is. There's 5th hour. I knew it was hidden in here somewhere. Let's look at our grade screen as usual. Let's see, get down here. We are on November 5th. That's this Sunday. Wow, because today's the last day of October. So what to do this week is the sum and difference of cubes and graphing quadratics. That shouldn't be too bad. You've dealt with quadratics for a couple of years. That's nothing new. Sum and difference of cubes is a little new stuff. We have looked at the difference of squares, but now we're going to look at cubes in that. So 3.03, 3.04. Let's go to our activity screen. Here it is, 3.03, sum and difference of cubes. So a little different than the difference of squares, but it does have some shortcuts that we can use just as well. Now, but to think about what a cube is, a perfect cube, which we can also just call a cube because all cubes are perfect cubes. If it's a cube, it's a perfect cube. It's a 3-dimensional object whose volume is found by multiplying the length, width, and height. Of course, in a cube, the length, the width, and the height, they're all the same number. That's what makes it a cube. So it's really just the length cubed or the width cubed because they're all the same number. So if their length, width, and height are not equal necessarily, we call it a rectangular prism, like a box. Most boxes are rectangular prisms because it's not a square, it's a rectangle. If it's a square prism, it's a cube. So there are boxes that are square and that are cubes, but most boxes are like rectangular prisms. So they want us to just practice off the start just to make sure we know the difference between a perfect cube and a rectangular prism. So they put like a stack of bricks. Bricks are not cubes. They're usually longer than they are wide and longer than they are tall. So we're going to put that in the rectangular prisms category there. Dice are obviously cubes, right? They have every side is the same. Although I do have a pair of dice at home that are not cubes. They're really weirdly shaped. And somehow, interestingly enough, they still randomly have the same values. If you roll them, you'll randomly get the same numbers as real dice. It's kind of funky. I should bring those sometime. But yeah, they're at home. Okay, a book. Well, a book's obviously not a cube. That'd be a really, really thick book for it to be a cube. Usually it's not the same height as it is wide anyway. They're usually not a cube, not even a square shape. So definitely a rectangular prism. These are some little fancy boxes that are built as a cube. Look, we can see that the length and the width and the height are all the same. So we put the perfect cubes. Oh, these are sugar cubes. So if you drink hot tea or anything, or maybe put these in your coffee, you might recognize sugar cubes. So those are cubes. And oh, this is just a long box. Almost looks like it could be a coffin, but no, that's like a briefcase. That's a briefcase. So we'll put the briefcase in the rectangular prism. So great job. They made that real easy on us because those things weren't even close to cubes. So, but we know what a cube is because we've seen dice or some of these other shapes. We know what a cube is. You may know what a Rubik's Cube is because it's actually named a cube. All right. So after this lesson, here's our essential question. Using the structure of the expression given, how can sums and differences of cubes be factored? All right. So familiar factoring patterns. So we've seen the difference of squares, right? T squared minus 4. We've learned that factors as t minus 2, t plus 2. That was a little shortcut. If we recognize that those are both squares, 4 is 2 squared, t squared is t squared. We recognize they're both squares, and it's a difference. It's subtracting. Then we can just factor it t minus 2 plus t plus 2. Just taking the square root of both of those numbers or items or terms. Terms would be correct. We've learned about perfect square trinomials to where if we see this pattern that if you take the square root of 36, which is 6, and double it, 12, oh, this must be a perfect square trinomial. So we'd factor a t plus 6, t plus 6. Because we see that the square root of 36 is 6. And if you double the 6, you get 12. So this has the pattern of a perfect square trinomial. And all the signs are positive. Or, if this was negative, it'd be t minus 6, t minus 6. But we recognize those. So we have a quick shortcut to factor those. And then just generally a trinomial, just like a quadratic equation, we can factor it, a lot of them. Some of them may have imaginary solutions or complex solutions, irrational solutions. But a lot of them we can just factor. T plus 2 times t plus 5 would equal t squared plus 7t plus 10. So those are ones we've done in the past. But now we're going to get into this. Like t to the third minus 27. Now that looks a little bit like the difference of squares that we've already studied, right? Because like t squared minus 9 or, x squared minus 16, But if we look at this, is t third a square? No, obviously not. It's a third power. Is 27 a square? No, because let's see, 4 times 4 is 16, 5 times 5 is 25. That's almost 27. So 6 times 6 is 36. No, it jumps right over it. So it's somewhere between 5 and 6. But if we look at this, this is t times t times t. So that is a cube. And negative 27 is a cube. I'll put this on paper real quick. So t to the third minus 27. This is a cube, t times t times t. And negative 27 is a cube. It's negative 3 times negative 3 times negative 3. Nice. So these are both cubes. So this is a difference of cubes. Difference of cubes. We will also look at if this was t to the third plus 27, that would be the sum of cubes. Remember, with the difference of squares, we could do difference of squares. We could not do sum of squares. Sum of squares, there's no shortcut pattern for that. It did not factor. Cubes are different. Both of these will be valid. We'll be able to do a shortcut for both sum and difference. of cubes. But let's get back and see what that shortcut is.
Like what kind of sugar?
So here's where it says that the t times t times t is t to the third. Negative 3 times negative 3 times negative 3 is negative 27. So the cube root of negative 27 is negative 3. We also see like 8 is a perfect cube because it's 2 times 2 times 2. Or negative 8 would be negative 2 times negative 2 times negative 2. So the sign goes with it. If it's a negative, its cube root is negative. So on this, if we put it in like a cube shape, it'd be a 3 foot by 3 foot by 3 foot. And that would be a volume of 27, right? Because the volume is length times width times height, 27. But let's get back to looking at this trinomial. They put a little video here that is 1 minute and 18 seconds that they'll go through this for you. And I'll show you this on paper, and you can watch that video later if you like, but I'll work through this one on paper. So let's go back to this p to the third minus 27. Okay, so I've got difference in sum of cubes. All right, so if we take the cube root of each of these terms, cube root is t. Cube root of this is negative 3. This is how this will factor. We can take the t minus 3, and that is one of the factors. Just by taking the cube root, that is one of the factors of this binomial. The other one, if we square this, t squared, negative 3 squared, that's part of it. The other part, we take these and multiply them together, and we change the sign. T times negative 3 is negative 3t, right? Negative 3t. We just multiply them together. But if we change the sign, that is the other factor. Well, that seems pretty simple. Yeah, it really is. The hardest, trickiest part of it is remembering that whatever sign is here, the opposite sign should be there. That's the trickiest part of it. This will be the exact same sign. Whatever those cube roots are, we're taking the cube root right there, p and negative 3, that's what the first factor is. The second factor, and this does not factor. Well, you can use the quadratic formula and find out it may have some irrational number that's the solution. T equals 1.68 or something, something really weird. But it's not going to factor as just a nice binomial or anything, two binomials. So this is the factors of this. Oh, wow. So what about this one then, the sum of cubes? We can do the same thing using the same pattern. So for t to the third plus 27, the first factor, here, we'll put it right here. First factor would be t plus 3, because the cubed root of this is t, and the cubed root of this is the positive 3, so t plus 3. And then using the same pattern we saw here, t squared minus 3t plus 9 is the other factor. And again, making sure these signs are opposite. The only thing that's consistent is this is always a plus 9 at the end. That's always a plus. This is always a plus. These do not change. Every time that's going to be a plus. Does not change.
William, are you agreeing with us? Nice, sucker.
So we can factor the difference of cubes and sum of cubes using this fancy little pattern right here.
Yeah, because it's going to be together.
So
at no point am I saying, hey, let's memorize the periodic table. But we're going to use
I'll put the little arrows to connect them. So if you're doing notes, this goes with this, this goes with this.
C6H12O6 is glucose.
All right.
Okay.
Does that look simple? Yeah, it's not bad. It just takes a little practice. When you do a practice, you're like, oh, well, this isn't bad at all. The only thing you have to do is you have to identify, are these both perfect cubes? And then just pay attention to that sign. So let's look what there's. So they do that. They go through that cube root. So there's the same factors they came up with. T minus 3, t squared plus 3t plus 9. By squaring those things. All right. Wondering why the middle term of the trinomial always has the opposite sign? Well, here's where they check it. Because you can check it by multiplying those back together. If you multiply factors back together, you should get the original. So I said, okay, so what happens if we made the same sign? T minus 3 times t squared minus 3t plus 9. If it had the same sign, when you worked it out, t to the third minus 3t squared plus 9t, once you distributed everything, those middle terms would not cancel out, and you'd have an entirely different equation. Because you would have a negative 3t squared up here, and then a negative 3t squared here, when you multiplied the t times negative 3t and the negative 3 times t squared. So it doesn't work if it's the same term. It has to be the opposite sign right there. So yes, it is that simple. Just watch the sign. That's where it gets tricky.
So it says,
all right, so sum and difference of cubes. Here is that exact same thing, just written a little differently. So let's use this in our notes. So a to the third plus b to the third. All right, this is the sum of cubes. Here's how the pattern works. Whatever a and b are, as long as they are cubed. See, we can rewrite this. This is the same as t to the third minus 3 to the third. Or the minus can be in the other side of parentheses. But we can say it's to the third power. 3 times 3 times 3 is 27. So you can rewrite it as the sum or difference. A to the third minus b to the third. So yeah, we should do that. T to the third minus 3 to the third. So we can see those are both cubes. This one is t to the third plus 3 to the third. So that gives you what your a and your b are. In this case, a is t, b is 3. So this one factors to a plus b. Whatever a and b are, since this is a plus, this is a plus. In this case, a was t, b was 3. So it'd be that. This one is a minus b. Since this is a minus, this is the minus. So you know the first factor. That's the first factor. The other factor follows a similar pattern. You take the a and you square it. Since this is the plus, you subtract a times b. And then you take b and you square it. There's how it works. A minus b, a to the cube minus b cubed. You square this. This time, since that's a minus, this is a plus. A times b plus the b squared. So you can see the only difference between the two is just the signs of the first two times they occur there. That's a plus, so that's a plus, and that's a minus. That's a minus, so that's a minus, and that's a plus. That's the trickiest part, is making sure you have the signs right. So up here we saw we had t and 3, and it was a minus. So we use this formula. So that means it's t minus 3, t squared plus 3 times t plus 3 squared. T squared plus 3 times t plus 3 squared. So if you want a nice general summary for your notes, this is it right here. Sum of cubes, difference of cubes. This is the pattern. So that works for any cubes, A and B. You just have to make sure it's a cube first. All right, so that's what this is right here. It's giving you the same pattern. So you can use these patterns to factor that. So investigate the signs of the original factor forms. Plus, minus. And that's what it talks about here. The sign of the original expression is the same as the sign in the binomial and opposite of the sign in the trinomial. And the second sign is always positive. Always positive. All right. So here's a little quiz. And you can put this in the chat. So I'm going to give this is participation time. Got some expressions. We're starting with this one, a to the third plus 64. And what we want to know, is this a sum of cubes? Is this a difference of cubes? Or is this neither one? Because we have to know when we can use these patterns. We can only use these patterns when we have a sum of cubes or a difference of cubes. So, a to the third plus 64. And you say a to the 3, not quite. Because 3 times 3 times 3 is 27. Oh, but you're a to the third power. I see what you're saying. Yes. Let me see if I can make that a little bigger. Yeah.
So it says on the left.
There we go.
Observe the left pane.
There we go.
What do you think the bubble?
Yeah. All right. Making sure you can see that.
I look at this.
A to the third. There you go. Oh, what happened to it? Oh, I hit something wrong. All right. Is that better? Better for your screen? All right. A to the third plus 64. Is that a sum of cubes? Is that a difference of cubes? Or is that neither one? I'm seeing some. John said can't be a difference. Nope, it's not a difference because difference means you subtract. All right, so the consensus is this is a sum of cubes. Let's see. Yes, it is. What about this one? R to the third minus 25. I see a lot of differences. What's your A and B? Let me ask you that. A is R, right? R to the third. That's obvious. What's B? What number do you cube to get 25? What is the cube root? Neither. Oh, Sean hit it. This is a square. It's not a cube. This is a cube minus a square. So it is a difference, but it's not a difference of cubes. It's a cube minus a square. They did trick us. This is neither one. That's why we have to do this, just so we make sure we know when we can use these shortcuts. 36 plus y to the cubed. Does the order matter? As long as it's a cube minus a cube or a cube plus a cube, it doesn't matter what the cube is. You can put the exponent second. I mean the variable second. You can put the number first. It still would be this times this. So the question gets to be, we know y is a cube. Is 36 a cube? 36. Let's see. We know 6 times 6. We know it's a square. But is there a number? Now, I'll tell you a little cheater right down here. They give us a list. If you want to print this out or write this in your notes, here are the perfect cubes on the right. 1, 8, 27, 64, 125, 216, 343, all the way down to 1728. That's the first 12 numbers that are perfect cubes. You're right. 36 ain't on the list. There is not a number that we can cube to get 36. So that one goes to neither. So it does have this list down here. Because we might know a few of these, but we probably don't have 1331 memorized as 11 cubed. You probably don't have 1728. Now you might recognize 1,000 being 10 cubed, because that one's kind of easier. But 729, knowing that's 9 cubed. See, so it helps to have these in your notes or have this print out or just have some chart handy with these numbers. So this is neither, because 36 is not a cube. About 125 minus p to the third.
Sandra, what do you think happening?
125. P to the third's obvious. 125. Is that a cube? Bethany says this is a difference. She's convinced. Yeah, let's go and look at our chart if we're not sure. Oh, look, that's 5 cubed right there. 125. It's 5 times 5 times 5. So yes, this is a difference of cubes. X to the third plus 8. Well, that's a nice little small number. Do we know that one? Wait. Bethany believes it's a sum of cubes. 2 times 2 times 2 is 8, Sean. That makes that 2 cubed. So that means this is a cube and this is a cube, because that's 2 cubed. That is a sum of cubes. All right, good job. Good job. We got them all. All right, I'm going to make that smaller again so we can see more of our page. And I'll leave it a little bit bigger. There we go. So, but there's that chart again. You can copy this in your notes if you want. 1 cubed equals 1, 2 cubed equals 8, 3 cubed equals 27. All right, but this is the first 12. And generally, they won't give us problems bigger than 12 squared. Hopefully. I don't think I've seen any that are larger than 12 squared. So generally, if you know these first 12 and have those somewhere, but you can always put it on a calculator. Like here's the calculator that's included with my computer. And it does have, now see, this is square root. If I go to, I don't know if I can make it any bigger or not. Oh yeah, I kind of can, but it still didn't make these things here any bigger. If I go to the second button and shift, basically, now it's got a cubed root right there. And this has any root I want. It has the X to the Y root. But yeah, when I hit the second button, it changes to a cube root. So I can hit 8 cube root, and it tells me it's 2. 2 times 2 times 2. So a lot of calculators do it. You may just have to look it up and see what it looks like. But usually there's a third root button. You may have to shift to get it on most scientific and graphing calculators. So, but like I said, I don't think they'll generally give us anything more than the first 12 for the most part. All right, let's go to our next page.
But at the same point, if I drop my light,
Factoring the sum and difference of cubes. So now that we know the rules, let's put them to work. Factor this completely. 2z to the third plus 1. Okay, so I'm going to do this one because they're kind of throwing a curveball at us if you're not paying attention. 2z to the third plus 250. So can we use our shortcut of sum of cubes on this problem? Well, here's where they throw us a curveball. This is a sum of cubes problem. You're like, what, 2? How am I going to take a number and cube it and make it 2? Well, we have to remember anytime we're factoring, step number 1. Step number 1. And it doesn't matter if it's difference of cubes, sum of cubes, if we're doing a quadratic equation, it doesn't matter. Greatest common factor is first. Always look for that greatest common factor. Sean, you're right on top of it. If we factor a 2 out, now we have a z to the third plus 125. All right, we can say y equals whatever. Factor a 2 out because both of those have a 2. Now this looks a lot more like a sum of cubes. So we can factor this to 2 times, what's our a and b? A equals z. B equals 5. 5 times 5 times 5. So this is z plus 5 times, now we go to this one right up here, z squared minus, since this is a plus, minus 5z, and then square the last one. That's why this is always a positive, because this last term is squared. And every time you square something, you end up with a positive answer. So that's why we know this will always be a positive. And the first term here is always a positive. Never have a negative x squared or anything, negative z squared, because you're squaring those numbers. So that's the answer. That is the factored form of this one. Didn't have to put the y equals because we were just factoring it. We weren't setting it equal to anything. So factor the greatest common factor, 2. See, so they rewrote it as 2 times z to the third plus 125. Identify the cube root, which for z to the third, it's z. And for 125, it's 5. And then use the pattern. Where's it at? There it is. So we get 2 times z plus 5 times z squared minus 5z plus 25. And then check your work. You check your work by multiplying everything back together. So they have that here. We click on it and it will multiply. First, it distributes the z to all 3. Then it distributes the 5 to all 3. Puts all those terms together right there with a 2 out front. When they see, this cancels out negative 5z squared with plus 5z squared. 25z cancels out with negative 25z. So it just leaves z to the third plus 125. And then you distribute the 2 and get back to the original binomial. So we know that is correct. All right.
Do not forget to do okay, let's jump down to that.
All right. Don't forget, coefficients are typically written before their accompanying variables. You'd write, 64 y third. We wouldn't put y to the third 64. Coefficients go ahead of that. All right, factoring completely here. Let's do that one. 64 y to the third minus 729 z to the third. That's a good one. Got to move my Weird Al mug. Yeah, he's in the way. Move over here, Weird Al. Okay. Get to that farther. 64 y to the third minus 729. So if this is a difference of cubes, first let's look and see, does anything factor? Like greatest common factor out of it. This is an even number, this is a non-number, so 2 ain't going to come out of anything. What are the factors of 64? Now 64, we can take it down to 2 times 32, which we can take to 2 times 16, 2 times 8, 2 times 4, 2 times 2. It's all 2s. 2 times 2 times 2 times 2 times 2 times 2. 729 is actually 9 times 81, which is 9 times 9, which this will be 3 times 3 times 3 times 3. These are all 3s. There's nothing in common. This is all 2s, this is all 3s. Nothing. So this does not have a greatest common factor. So is this a difference of cubes? What is the A? What is the B if it is?
I want to know how temperature affects it.
So what is the A? If this is a difference of cubes, which we believe it is because nothing can factor out of it, so these must both be cubes. What is our A for 64y to the third power? A would be whatever we're cubing, right? What would we take times itself 3 times to get that? It's kind of a combination of both, Sean. What do we multiply times itself 3 times to get 64y to the third? 64y to the third would be what times itself 3 times? Multiply something times itself, and we'll end up with 64y to the third. So 4 times 4 times 4 will give us the 64. What will give us the y to the third? Y. So 4y times 4y times 4y equals 64y to the third. Because 4 times 4 is 16, and 16 times 4 is 64. So A is 4y. You got a y with a coefficient of 4. So yeah, don't get that confused. If you see 64y third, it's just a coefficient and a variable. 729z to the third. So B is, we go back and look at our chart if we need to, but I said over here it's 9 times 81, which is 9 times 9.
Okay, so we're answering A, B, and
So
C.
it's 9z. 9 times 9 times 9 is 729. That's on that chart they gave us, by the way.
Hey, Tucker, I need you back.
9 times 9 times 9, 729. So our A is 4y and our B is 9z. All we have to do is put it into the pattern now. A minus B. 4y minus 9z. Because that's what our A and our B is. So just putting it in the pattern. Now I got A squared. So 4y times 4y is 16y squared. Plus AB, since this was a minus. Plus A times B. 4y times 9z is 4 times 9 is 36. And then I have a yz. Because that's what multiplying those two together will get. And then the b squared. 9z squared, which is plus 81z squared. It's a big day for scammer telemarketers. That's the answer. We just use this pattern. All we have to do is identify what A and B are. What do we cube to get 64y to the third? And what do we cube to get 729z? And then it's just making sure the signs are right. I mean, technically, we could say this is negative 729. It's a negative 9z. But as long as we put the right signs in there, we're just looking for what is the actual number. 729 is a 9.
I have it in the chat if you want to grab it and put it in yours.
So there we go.
Fill in those blanks if you're getting a little stuck.
So just take it simply and just follow the pattern and just multiply it together. Yeah, when we multiply y times z, we get yz. 4 times 9, we get 36. Don't make it complicated. It is pretty simple. The hardest part is really identifying what A and B is. Taking the cubed root. And then it's a matter of just simply plugging it in and getting the signs correct. But getting the cubed root. And that's not even terribly tricky. It's easy if you have y to the third and z to the third, because you know that's just y and that's just z. It's these. As long as you use that chart, you should be able to get the numbers. And if those numbers aren't on there, see if you have a greatest common factor you need to take out. Because 250 wasn't on that chart either. 250 is not a cube. 2 is not a cube. See if you can pull out the greatest common factor. And then it might lead you to have that cube.
So there's a 3B sentence.
So this one had factor the greatest common factor. Does it have one? No. That's what we looked at. 64 and 729 are divisible by many numbers, but none of them in common. So there was no greatest common factor. That's one we just did. The cube root of 64 is 4. The cube root of y to the third is y. So you got 4y then as A. 729 is 9. Z to the third is z. So B was 9z. And that's what we came up with. We came up with 4y and 9z. And then just use the pattern. 4y and 9z. Use the pattern and end up with that answer right there. And again, multiply those back together. And it will cancel itself out. And you'll see, oh, yep, that works. That is the right answer. Here's another example if you need that. I'll leave that for you. It's no, you can practice this one on paper. Oh, we will look before I leave that to you. We will find the A and the B together on that. But I won't work the whole problem. I'll leave that for you to do and check. I do want to look at that because that is a little different. A, B. Wow. Z to the 12th. What's our A going to be? What do we multiply together times itself 3 times to get Z to the 12th? That's why I wanted to do this one. This one's a little bit different. We've been dealing with Z to the 3rd, which we know is just Z times Z times Z. But now we don't have Z to the 3rd, we got Z to the 12th, which you will have problems like this, that it's not to the 3rd power, it's to a different power. In this case, to the 12th power. We know it's got to be a Z something. We know it's a Z something, but what is it to get Z to the 12th? What power of Z? Z to the what times Z to the what times Z to the what equals Z to the 12th. Sean says it's a 4. Lindsay says it's a 4. Remember, when we multiply exponents together, if we go back to our exponent rules, this is the same as Z to the 4 plus 4 plus 4. When you multiply them, you add the exponents. So 4 plus 4 plus 4 is 12. So yes. A is Z to the, I'm not, it's not Z to the 12th. That was what we started with. A is Z to the 4th. What's B? Oh, that was the very bottom of the chart. That was 12. So there's your A and your B, Z to the 4th and 12. So you can do the factors from there. I'll leave that for you to practice because they give you the answers there where you can check. We factored the greatest common factor, which was none. We found the cube root, Z to the 4th. Say they did that. And then I'll let you do it, substitute it in the appropriate pattern, see if you get the right answer, because you can double check it right there. That is right there under the Learn More tab. So if you want to do that and check your answer. Lesson summary right here. We're at the end of the sum and difference of cubes lesson. Has those 2 patterns for sum and difference right there. And it talks about the steps. Factor out the greatest common factor. Identify the cube root. And then substitute into the pattern. What's the A? What's the B? All right, so that's not too bad. Not too bad. Now let's look at the assignment that goes with that. Oh, so this is which of the following is a factor? And it gives you this. X to the 3rd minus 1331. And it gives you some choices. Is this one of the factors? Is this one of the factors? Is this one of the factors? Or did we not list any of the factors? So you would find the A and the B, substitute that into the pattern, and see if this is one of the items that's in that pattern. Here's another one. 6x third plus 6. Oh, well, right off, I know one of the factors. One of the factors is 6, because I can factor a 6 out. But that's not one of my choices. They didn't list the 6. So obviously there's more factors, because that leaves x to the 3rd plus 1. When I factor out 6, x to the 3rd plus 1. X to the 3rd is the cube. 1 is a cube, because it's 1 times 1 times 1. So you should be able to get that. Which is the factor of this? Which of the following is a factor of this? And which is a factor of, oh, there's a really big number they gave us at the end. 50108y. So 500x to the 3rd and 108y to the 18th. I'm thinking greatest common factor is coming out of that, because 500 is not on that list. It is not a perfect cube. So you're going to have to pull a greatest common factor out of that. But that's it. 5 questions. Yes, I know I haven't done it yet. All right, let's look at our other lesson, graphing quadratics. This shouldn't be too bad because this is not your first exposure to quadratics. You've done those previously in other algebra classes. Talks about parabolas in your life. We're surrounded by parabolas. You just may not notice them all the time. But, you know, these are parabolas underneath this bridge. The dish you see at people's houses, that's a parabola shape. It's a very wide parabola, but it's a parabola. Water, the sprinkler makes a parabola shape. The Eiffel Tower has parabolas built into it for structural reasons. Parabolas do great to hold weight. That's why they're used in architecture. And when you kick a ball, it makes a parabola. It goes up, has a vertex, comes back down. And they'll show you those parabolas right here in red. So yeah, parabolas, different sizes and shapes of parabolas. All right, so our essential questions we're going to learn. In what way does adding a constant or coefficient affect the graph? How are the axis of symmetry and the vertex related? And what's the key features that we can identify of a quadratic graph?
There we go. Our plants alive.
So quadratic equation.
Okay.
So they took the quadratic equation, f of x equals x squared. That's just the parent function without any changes. They made a table. They said x equals -2, -1, 0, 1, and 2. So the y equals 4, 1, 0, 1, 4. And then they graph those points off that table. So when they graph those points, it makes the parabola that we expect on x squared. That is the f of x equals x squared. This is very common, we're very familiar with this graph. It's a parabola in standard position without any changes. But if the variable x is multiplied by a number, how would that change the graph? Well, let's go look at that. Y equals x squared. Okay, let's put that in the middle. What if we put a number in front of that x? What if I put a 5 in front of the x? How is that going to change our parabola? That'll be 5x squared. What's that going to look like? How will the graph change? Okay, so Sean says if you do +5, it would move it up. He believes. So that would be at the end. If we just add a +5 in the end. +5. You're absolutely correct. So that's important to know too. If we just add a number on the end or subtract a number, that would move it down, right? If we subtract it. So that does that. So, okay, so we know if we put it at the end, but if we put it at the beginning as a multiplier, so we know it's not going to move it up or down because that's adding it at the end, not multiplying it in front of it. I'll give you one hint. Let me put a point on there that's on this graph. So if I go here and I say 1, 1, that's a point. That's one of the points on this graph.
I will be able to create
as well as -1.1.
So it says we're not going to play with it yet. I want you to tell
-1, 1. I
in
mean,
the gizmo what.
So if I substitute x equals 1 into the equation equals 1. The y equals 1. So I graph that. If I substitute -1 and I square it, it equals 1. So if I put a 5 in front of it, let's just do it. Nobody's really sure. Nobody's confident enough to put an answer in the chat. So let's just put a 5 in front of it. If we put a 5 in front of it, oh, look at that. What happened? It gets skinnier. It goes up a lot faster. Because now it doesn't equal 1 anymore. When I substitute 1 in the equation, it used to equal 1 because 1 squared is 1. But now I have to multiply it by 5. So now when I substitute 1 in, I get 5. So I have a new point that is on the graph, the 0.15, because I multiply it by 5. Make it ascend faster, yeah. We generally say it's stretched because when we talk about shrink, it's stretched vertically. It's pulled up faster. Shrinking, we usually think about if we put in a number like 0.5. Now we shrunk it down. It's instead of being up here at 1, that point moved down here to a half. So it shrunk it down. It's not as high as it used to be. It's at a half. So this is generally stretched. Instead of when I put 1 in for x, instead of it being equal to 1, now it's equal to 5. We stretched it up to 5. Now, if we're talking about horizontal, it's shrunk, but generally we're talking about vertical. Up and down, we stretched it up. Makes it ascend faster. Yes, it goes up exponentially faster because now it's going up 5 times as fast as it would. Would -5 make it very wide? Very good question. Let's see what -5 does. No. It still does the 5 to make it skinny, but it just reflects it downward. The -5 reflects it downward. So the only way to make it wide is to divide it by 5 instead of multiplying by 5. So that means if I divide it by 5, instead of 1x squared, it'd be 1 divided by 5x squared, 1/5. Let's put 1 divided by 5. There's 1 divided by 5x squared, which we could also call that as a decimal, y equals 0.2x squared, right? A decimal 0.2. The 0.2 is the same thing as 1/5. 1 divided by 5 is 0.2. So that's the same. It's the same graph, 0.2 and 1/5. So yeah, if I put a number that's smaller than 1, that means I'm dividing it. Smaller than 1 is going to make it wider. And again, if I make that a negative in front, it just reflects it down. That's all the negative is going to do, just reflect it down. But the smaller than 1, a decimal number, 0.5, 0.68, anything like that is going to make it wider. So put a whole number in front of it, like 10, it's going to make it real skinny. Put 0.10, it makes it really wide because it's smaller than 1. All right, I like that. You guys get a good idea on what that's doing when we put the number in front of it or if we put the number behind it. But what about if I put the number with the x? Instead of x, I'm going to substitute x plus 4 in for the x. It's not going to be x anymore. It's going to be x plus 4, and that's going to be squared. Is that going to move it up 4? We know it's not going to make it skinnier because that's multiplying it. Oh, would it make it go up to 0.16? That's a good question. Okay, let me turn this one off. If we did y equals x squared, and then we did it afterwards, plus 4 squared, that would go way up to 16. But it's afterwards. But I'm going to take it and put it inside the parentheses with the x. So I'm adding it to the x first, and then I'm squaring it. I'm not going to square it afterwards. So I'm taking that one back off. If I put plus 4 inside with the x, plus 4. Oh, it moved it over here. It moved it left. It moved it left to -4. So if I take out the x and put in an x plus 4, it moved it to the left. If I put an x minus 4, yep, you're on top of it, Sean. Minus 4 moves it to the right. It does the opposite of what we think. Well, if I do minus 4, that's going to move it into the negatives, right? No, it moves it over into the positives. That's the only time it's backwards is when you take the x out and put an x plus or minus something. It goes the opposite direction. Because if we put minus 4 on the end, it will go down into the negatives. Well, negative x move it down. Actually, negative x, and if I take the 4 away, you can't really see this. Negative x, it doesn't look like it did anything, but it actually did. It took 1, 1, and it moved over here and made it 1, -1. You can see that if I put x minus 4, and I make it a negative x, it's going to reflect it over the y-axis. Negative x minus 4. Negative x moved it over the y-axis. Putting the negative way out front moves it over the x, moves it down. See, over the front out there. But if I put the x inside the parentheses, so yeah, the negative out front will make it go downward. But if I put the x inside the parentheses, I put a negative x, it makes it bounce over the y-axis. So different ways to move it around. If you're not sure, you can always go to Desmos, put in an equation and play with it like I'm doing right here. Just go in there and say, oh, what would happen if I do this? Oh, it moves it that way. Got it. Okay, I understand now because I can see it with my own eyes. So, all right. So that's what this is talking about. A multiplier. So it's doing things like that and saying x minus the number. So that leads us, I'm going to go to my paper here. That leads us to look at all the different things that just happened there. Let's say f of x. We'll call f of x. If we put a number out front, we know what that does. It makes it bigger. If we put a number inside with the X, we know that moves it left and right. If we put a number outside, we know that moves it up and down. Right. This just makes it shrink, skinnier or wider, narrower or wide. This will move it left and right, and this will move it up and down. So if H and K were 0, we're both 0.
Okay. But you also said, can I finish?
Then we know it's not moving left and right. It's not moving up and down. And the vertex is going to be at the origin. And we can actually go to Desmos and put in equations that look like that. Let's take this away. So if we say AX minus 0, I'm putting 0 in for H squared plus 0. I got to add a slider. So right now, A equals 1. Excuse me. A equals 1. So that's just a normal X squared equation because we added and subtracted 0 from it, and we added and subtracted 0 at the end. So we didn't change the X or K. If we change that to a 1, where's the vertex? It moved over to 1. We change this to a -2, same thing as -2. Where'd the vertex go? It's at 1, -2. There's a secret here in looking at the formula. This is known as the vertex form.
Yeah, I need you to come in.
This is the vertex form of a quadratic equation. The standard form, that's what we're used to seeing. Standard form is AX squared plus BX plus C. That's what we're used to seeing. 2x squared plus 3x plus -1. That's what we're used to. That's the standard form.
Yeah.
But this is called the vertex form. Why do we call it the vertex form? Oh, because let's look at it. Let's look at the sample. If we just have X minus 4 squared plus 1, what's the vertex?
So, 6th period, guys. I'm going to jump over to 8th.
4, 1.
So remember, Thursday morning.
What? How'd you do that, Mr. Brock? We didn't even graph it.
Send an email as a reminder.
The vertex for the vertex form
Hunter, are you okay?
is HK.
Okay. I will see you guys later. We're going to write checks today.
HK. For this equation right here, H and K tell me what the vertex is. That's the turning point. That's where the middle of the parabola is. X minus H plus K. X minus H. H is 4 plus 1. So let's look at that. Is that really the vertex? X minus H. Oh, let's see. All right, let me take all that out. Take out the slider. I don't need a slider. So I said the equation was X minus 4 plus, did I do plus 1? I did, plus 1. Oh, I didn't do squared. Squared. X minus 4 squared plus 1. Oh, look what the vertex is. 4, 1. That's just what I said it was. The vertex was 4, 1. Just looking at this equation. Because the H and the K tell me exactly. And that shouldn't be hard to understand because we know it starts right in the middle. And we know this moves it left and right. So X minus 4 means I moved it right 4. And I know this moves it up 1. So if I start at the origin and I go right 4 and I go up 1, I'm at the point 4, 1. So it really works nicely instinctively. If we go from 0, 0 to 4, 1, we went right 4 and we went up 1. So this is how we would have to change our equation. Now, when does this get tricky? Because that looked really simple. I just took the 4 into 1 and said that's the vertex. When does that get tricky? Okay, this might be a little tricky. I'll write a different equation and see if you can put the point in the chat of what the vertex is. X plus 5 squared minus 2. What is the vertex of this equation? I'll leave that at the top of the screen, showing you the vertex form. 3
Hi, Sierra.
times x plus 5 squared minus 2. What is the vertex? What is the xy coordinate? -5, -2, says Sean. Anyone agree with that or have a different answer?
Haley, I don't know why. Every time it's just Haley Combs, it can't just be Haley.
Bethany agrees. I'll write that down for those of you who are looking at that. Is that right? -5, -2. Yep, Jonathan agrees. Yeah, that's when it gets tricky, when this is a plus. Because this is still x minus h. So the only way you can get plus is h must be -5. Because x minus -5 is the same thing as x plus 5. So h equals -5. And the k is just the k. That's an easy one. If it's +2, the k is 2. If it's -2, the k is -2. That is the vertex. Absolutely correct. And we don't care about this. That just changes the shape of the parabola. Is it wider or skinnier? That has nothing to do with the vertex. I just threw that out there. Nothing to do with the vertex at all. Good job. Fabulous. This is correct. Just watch out for the sign. If it's negative, then you just take the h. It's just a 4. If it's positive, you got to remember, okay, it's subtracting it. So how is it a positive? Well, it must be subtracting a negative. Great job. You guys, oops, killed too much here. You guys are on top of this. All right, so I won't go through the rest of the example. Let's see, more on changing the graph of parabola. Let's see if they tell us anything we don't know. I doubt it. I think we've got a good idea. Okay, what's the difference between the graph of 4x minus 8 squared plus 2 and the standard graph of this one? Well, that's not too hard. 4 means it's skinnier because we've made it grow faster. -8 means it moved right 8. And plus 2 means it went up 2. So the vertex is going to be at 8, 2 instead of at 0, 0. It's going to be way over here and higher.
Yeah, what's everyone mean? Okay, it's a good question.
Oh, there it is. The vertex is at 8, 2, and it's skinnier than this one here. It moved right 8 up 2, skinnier than that. Yeah, we can do that. -1/3 x plus 1 minus 5. The plus 1 moves it left. The minus 5 moves down. So we expect it to be down here is the vertex. It's less than 1. It's divided by 3. It's going to be wider, but it's going to be facing down because it's got a negative out front. There it is, a negative out front, and it's moved down over here. All right, you guys got this. I think you got a pretty good grasp on that.
Okay, I'm gonna take pictures.
And this just breaks down each piece individually that we've already talked about. Putting a plus c inside with the x moves it left and right. Plus c at the end, up and down. Doing a c with the x just makes it wider and narrower. Putting a c out in front makes it wider and narrower, but could, if it's a negative, makes it go down. So, and number multiplied by the whole function, you would just simplify it first. Like 2x plus 2 times 3 becomes 6x plus 6. Just a practice for you. I won't do all of these because this is where you can check to see if you understand. We'll do the first one. Tell you what, there's 7 of them. So let's do the first one. So choose the correct option. Does this open up or open down? Well, the equation is -2 x minus 4. Make this one a little bigger because we can make this bigger.
I know, right, Miss Miller? Like, there's no way.
-2 x minus 4 squared plus 3.
No.
Well, first thing I see is a negative, which tells me this opens down.
No.
Is this narrow or is this wider? There's a 2 out front. That's bigger than 1, which means it's going to be more narrow than a normal. Okay, there's a plus 3 at the end. That tells us if it moves up or moves down. So this moves up. And we have an x minus 4. We got to remember that works opposite. So if it's a minus, it moves right. So we can say, okay, there's all the options. Submit. Correct. So there's got 7 of those for you to practice to see, do I understand what it's asking?
That means we're meeting today.
So there you go.
And we are meeting Friday.
All right.
Okay.
Let's see what else we have in here. We've learned a lot about graphing quadratics already. Parts of a parabola, the vertex, axis of symmetry, domain range, and sometimes the x and y intercepts.
Some of us, we will be meeting today.
All right. So finding the vertex, when it's in vertex form, is very simple. Right, we got that.
We go on quarters.
Quarter
reset a few weeks ago.
Let's talk about when it's in standard form, because that's where it varies. We can do vertex,
So some of us are grade
and we can do axis of symmetry. You're like, what is the axis of symmetry? Well, let's see. Do I have a graph of a parabola yet? No, let's make a graph of a parabola.
kind of like a test.
If we have a parabola, this graph paper is what's printed on page 1. You could print graph paper. If I have this parabola, and the vertex is right here, that's the vertex, and it opens up, and it's just standard width. All right, so okay, so that's just a standard parabola. I drew that close. It's off a little bit. Actually, this side should go over to that point there. It should go to 1, 1, 1. There, let me fix that a little bit. All right. Vertex is at 1, 2, 3, 1. The axis of symmetry. Symmetry means it looks the same on the left and the right, right? Like this eraser has a symmetry right in the middle. Well, if I turn it over and don't have the logo, this side looks like that side. This side looks like that side. Symmetry, cutting something exactly in half. You have symmetry. Well, so the axis of symmetry for this would be right here. Right? That line is the axis of symmetry. And if I drew that correctly, which I'm not sure I did, it'd be exactly the same both ways. Like if this is 1.5 away, then this is 1.5 away. Because it's like a mirror image. Symmetry is a mirror image. So this is known as the axis of symmetry. And it's really easy to get the axis of symmetry, especially if you have a graph. What's the vertex? 3, 1. So what's the axis of symmetry? It's the line where x equals 3. I just used the first number, the x. This is x equals 3. Right? Doesn't matter where the y is, the x always is 3. So this is the axis of symmetry.
So what I want you to do, you're going to open up that top one first. It's not an assignment,
right.
It's information. Top one that says non.
We got the vertex, we got the axis of symmetry.
Phenomenon.
Domain and range. Let's talk about domain and range. The domain is all the possible x's, right? So the domain, this is going to keep going forever that way. This is going to keep going forever that way. Slowly, it's going up faster than it's going right, and this is going up faster than it's going left, but it's still going to go forever. So all real numbers. All real numbers is the domain. What's the range? The range, remember the domain is the x's. The range is the y's. Well, this y never gets below this point. That's the smallest y it will ever have, because this is only going up. So the range is y is greater than or equal to, because it does touch that point, the vertex 1. So I can get the range usually if I know whether it goes up or down from the vertex. The only time this wouldn't work is if you have a sideways parabola. Then it's your x that's greater than or equal to 1. But for most parabolas, which are up and down, whatever the y is going to be either your largest or smallest number. If this is an upside down graph, if it's going down, it'd be less than or equal to 1. But there's the domain and range. When is it increasing or decreasing? Well, it's decreasing until it gets to there, and then it's
we're gonna
increasing
compile that into a project.
right there.
You and your flight crew must log their
So if we
observations
looked at those options,
as you reach a
increasing
destination travel log. As you work towards this goal,
when
you will be learning the following
X,
concepts. So,
it's always based on the X, so it's increasing from
if there's something there, you're like, yes.
3 to infinity.
Sun and moon, and talk about the
Starting at 3, it's going up, and forever it's going to be increasing.
eclipses,
Decreasing,
they put it in your brain now.
well, it starts at negative infinity, way over here, as far as we want to go. It's coming down. It's way up there, but it's coming down. It's decreasing, 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 all the way until it hits 3. When X hits 3, when it gets right there, it stops decreasing, and then it starts increasing from 3 on. So we only care about the X, and the X is 3 and on, and decreasing is from negative infinity all the way until it hits 3. See, was there anything else that they were talking about? Find the vertex. Oh, yeah, I was going to show the vertex of a standard. Oh, gosh, got off track there. Standard form. So y equals 2x squared plus 8x minus 3. Standard form. And we want to know what the vertex is. Well, if it was in vertex form, I could tell you real easy. But it's not in vertex form. But we can get the axis of symmetry. And if you remember what we just talked about, the axis of symmetry goes through the vertex. Right? It's going to go through the vertex. So that will tell us the x coordinate of the vertex. X equals negative b over 2a. Negative b over 2a. What do you mean b? Well, remember, this is standard form. A, B, C. Those coefficients. So in this one, a equals 2, b equals 8, c equals negative 3. Because it's just the coefficients. So the axis of symmetry is x equals negative 8 over 2 times 2. Negative 8 over 4, negative 2. Negative 2 is the axis of symmetry. X equals negative 2. So if I draw that line on my graph, I do have another graph. If I draw that line on my graph at x equals negative 2.
Ben, are you on a second screen there?
That's going to be the axis of symmetry for my parabola. I already know that just based on the formula right there. So how do I find where it is exactly? Well, that's not too bad. If I know the x is negative 2, so x equals negative 2 is my axis of symmetry. I can take that negative 2 and put it in my equation and see what is y equal when x is negative 2. 8 times negative 2 minus 3. I could put the negative 2 in parentheses. I just drew my parentheses too early. Negative 2 squared is 4. So 2 times 4 is 8. 8 times negative 2 is negative 16 minus 3. 8 minus 16 minus 3. 8 minus 16 is minus 8. So it's at 11, negative 11. So the vertex is at negative 2, negative 11, which is actually going to be off my graph. It's going to be right down here. Here's where my vertex is. Negative 2, negative 11. When will it cross the y-axis? When x equals 0, right? Because this is x is 0 on the y-axis right there. So if I put 0 into this equation for x, 2 times 0 squared is 0. 8 times 0 is 0, minus 3. That's our y-intercept. So we can say, okay, the y-intercept is going to be right here. Since this is symmetry, look at there. That's 2 spaces away. So I know I have another point 2 spaces away here. I can kind of draw my. Should go right to that point.
As the height between objects change, these are key questions I want you to, when you get it today or Friday, like, oh, let me go back.
There, I've sketched it. This is just kind of a sketch. It's
About potential energy. Remember the water bottle
because
example?
we didn't get exact, but we know some key points. We know the vertex, we know the y-intercept, and we know another point because it's symmetrical. Yeah, this is terrible. Oof, that should be sloping that way.
Taylor,
Yeah.
we have the third assignment.
Let's graph this and see what it actually looks like because we just pulled that information. We can get the domain and range. Domain's all real numbers. The range is y is greater than or equal to 11. We know it's decreasing. We know it's increasing. We know a lot of stuff about it. The only thing we didn't find was where does it cross the x? And we would do that by solving this by setting it equal to 0.
Let me put it in the chat if you want to steal it.
And then if it factors, which I don't think it does, this does not factor, we'd have to use the quadratic equation, the quadratic formula to find out what the two x's are because they're not going to be whole numbers. They're going to be irrational numbers. But let's graph this and just see what it looks like.
So if you need a sentence to start that page.
Right there. Okay.
Hey,
Get rid
Taylor,
of that
I
one.
need you to have that third
2x
We're on page 3.
squared plus 8x minus 3. Let's see. There's that y-intercept we said at 0, -3. The vertex is down here at 2, -11, just like we said. And see, here's the zeros. See, they're not nice integers. They're at -4.3.345, and this at 0.345. And this is probably a rounded number. It probably goes a lot more than that. So we would definitely have had to use the quadratic formula to figure out what those numbers were.
Please do it.
But we can do all of that just by having the standard form and using the axis of symmetry equation. That's good to have in your notes. -b over 2a from the standard form. So if you don't have the vertex form, which is real nice when you have the vertex form, you can start there, take that -2 that you get, substitute it into the equation, and find out what does the y equals.
Take that sentence in, even if you're unsure
Y equals -11, and that gives us our vertex.
Because how can you calculate it?
And we know it's positive, so we knew our vertex opened upwardly. There's a lot we knew. We were able to graph it just by having the equation and just a blank graph without having to use Desmos to do that all together. So they'll walk you through that right there. Vertex, axis of symmetry. Learn more about the axis of symmetry. Domain and range, we've talked about that.
Copy and paste it.
Additional examples on finding domain and range. The intercepts, that's where you have to solve it. Set it equal to 0. If it factors nicely, you'll get whole numbers. The one I made up didn't have a nice whole number. And of course, you get the y-intercept for that as well. Average rate of change is one thing we didn't talk about. And then I'm gonna wrap it up because we're about to run out of time anyway. Average rate of change. All right. Let's take this one just because we know what these points are.
That's one of our tasks today.
If it asks you for the average rate of change on a graph,
Page 3, 'cause I want to check at the end.
and let me just make a different one over here. I want to make a graph that goes right here,
All
right
so
here.
we're just gonna mentally set that tab aside for a second.
Okay.
Let's go back
Here's
to
my
our
parabola.
classroom.
Okay, I think I drew that one a little better. That looks a little more like a parabola. And it says, what is the average rate of change?
Before you click open the document, let's look at the
Average
instructions.
rate
So, if I just click it, it's got some
of
instructions.
change.
Don't see the document yet.
Average rate of change from between,
See your screen?
it'll say this, between x equals, let's see, x equals
The lengthy
4
potential
and
group team
x equals 7. So what's the average rate of change between x equals 4 and x equals 7?
So if you want to work
Don't make this harder than it is. Find those places where that is. X is 0, 1, 2, 3, 4. So this is right here. That's when x equals 4.
it's going to cover all the
5, 6. This is where x equals 7.
okay?
What is those points? What are those points? 4, 1,
You will be making a video.
7, 1, 2, 3, 4, 7, 4.
It's not a present to class video. Some of you are like,
It's asking quite simply,
it'll be one that I
What is the slope of the line? Average rate of change is the same thing as the slope. Between those 2 points, if we drew a line, which I'm doing right there, what's the slope of that line?
And if you want to do
That's what it wants to know. What's the slope of that line? Between x equals 4 and x equals 7. I don't care about all the graph. I just want to know between those 2 points, what's the average rate of change? Well, we can see on this, as it goes up 1, it goes over 1. Rise over run is slope.
as a puppet show, do a puppet show.
So it's 1. The average rate of change is 1. We could also use the y2 minus y1 formula. This is the slope formula. M equals. Where you take the second point, the y is 4, y is 1, divided by the y is 7 minus the y. The x is 7 and the x is 4. How much did it change? The x changed 3, right? It went from 4 to 7. It changed 3. 1, 2, 3. How much did the y change? The y went from 1 to 4. It changed 3. 4 minus 1 is 3. So if the x changed 3 and the y changed 3, that's just 1. The average rate of change was 1. The slope of that line is 1. It's getting all sideways on us. Slope of that line is 1. The y changed 3 and the x changed 3, so that's 3 over 3. Average rate of change. Don't let them confuse you when they ask for the average rate of change. So, all right, and she kind of puts it all together to another video if you need to watch that. Talking about these parabola of this basketball being shot. Talks about the axis of symmetry again. Identifying the elements of parabola, which we've talked about many times.
If we get to the very end,
If there's anything else we missed, standard form, we've already talked about standard form. There's that x equals negative b over 2a. Find axis of symmetry and go from there to get the vertex. Find axis of symmetry, vertex, domain, range, and intercepts. Okay, walks you through all that. All right, I think we've gone through everything that needs to be gone through there. It's repeating a lot of examples that you can go through, and there's the lesson summary. If you want to make notes off of that, gives you the vertex form, talks about what the vertex is, axis of symmetry, average rate of change, just find the slope, like we just talked about. Is it increasing or decreasing? Gives them more examples. So there it is. There's that negative b over 2a from standard form. All right, we're going to close that down. Let's look at the assignment real quick. Graphing quadratics. Identify the vertex, domain, and range. They gave you a vertex form equation. What is the equation for the following graph? Oh, I don't see a graph. Oh, if I reload, maybe it'll be there. There's supposed to be a graph. Hopefully it will load your graph. There it is. All right. What is the vertex form? Well, what is the vertex? Plug it into the formula for the h and the k. Which following represents the graph becoming more narrow? If we put a plus k on the end, if we multiply it by a k, if we added a k with the x or subtracted k minus x, which of those would more narrow? What's the average rate of change from x equals 3 to x equals 5? Oh, they're trying to fool you there. How much was your rise between those 2 points? And determine the axis of symmetry.
So you're part of a shuttle crew.
There's the vertex form. There you go, guys. There you
There
go. That's it. Rate of change equals the slope. It's exactly correct, Sean. That's exactly what I'm saying. Average rate of change means what's the slope? If you drew a straight line between those 2 points. All right, guys, it's almost time for advisory, so we better get out of here. You got to do your grade checks and your advisory classes, all that good stuff. So you've redone 1.07. All right, I'll get that in there so that way it'll reflect on your grade check, your new grade on that. So, all right, guys, got any questions? This is a B-Day Friday, so I'll be here Thursday and Friday. Have a great Halloween. Get a little candy. All righty. Bye-bye.